this is the second part of the 4-part series of how to fit diode data, specifically from a WITEC instrument, using the workflow that we use here at UC Berkeley. So we have already run our neon line correction model, and I recommend you watch that YouTube video first. And now we're going to start looking at the Spectra file, so our actual acquisitions of, say, melt inclusion vapor bubbles or fluid inclusions. So as normal, we're going to import all of our Python packages. And now we are going to load in our information that we saved in step 1. So if you remember at the top of step 1, we saved a ton of information of like what folder our metadata is in, what folder our Spectra is in, and what file types we're dealing with. So we're going to load them in here, and then the final thing you're going to want to do is list out all of the sort of names of things which they're not your diode files. So here we're excluding our neon lines, we're excluding acquisitions we took on the silica chip at the start of the session, we're excluding files where I labelled them no diode, they don't have a diode, there's no point in wasting my time fitting them, and various other things. Some of them I put no underscore diode, so that's why I've got that here. Okay, and now we're going to get our diode files. So we're looking in this Spectra path for the file extension for all of the files except those including this string. So you can see here is a list of the files that we are about to fit. Okay, so what we then do is we are going to tweak a function which helps us find the approximate position of the diode peaks. This isn't fitting void peaks to them, this is literally just using Scipy find peaks on the raw Spectra to say where approximately are the peaks. So the key parameters are, as normal, your Scipy find peaks parameters, so specifically the prominent and the width of the peaks. Okay, so we're going to run that, and then we are going to look at the first file, so just to see how this is doing. So you can see the algorithm has certainly found my peaks. It's found diode 1, it's found diode 2, and it's found the hot bands. It has also found an SO2 peak, you can see here. So you can just see if you were to adjust that prominence, you suddenly find a lot more peaks. That's not really ideal, you don't want to be finding this many peaks, but the algorithm can actually deal with it. The biggest problem is if you set this value too high. So if you set this too high, it hasn't found your hot bands. So if you wanted to fit your hot bands or your SO2, that would be less than ideal. So let's just put it back to 30 as a reasonable approximation. Doesn't matter too much, you just want to make sure it's finding the diodes and the hot bands. Okay, so that's for one file. Now what we're going to do is we're going to loop this Scipy find peaks algorithm over all of the files. And this is going to give us the approximate positions of the diode and the hot band in each Spectra file. So you can see here, the approximate position is this. If it found a hot band, it's given the position, otherwise it's put a nan in. Okay, final thing we're going to do is we're going to check for duplicates. You do not want to have named given the same name to more than one Spectra. When you go to merge that with your metadata, you're going to have a nightmare. So we are checking for that now, because if you've got it wrong, you're going to want to rename your files now before you go through the effort of fitting them. So you can see here, it's checked through all those names and it hasn't found any duplicates. Okay, quite often you'll see there are cosmic rays in your Spectra. Some Raman instruments can get rid of these automatically. So for example, Hariba does a really good job of that. WITEC, you have to do it manually in the software, not ideal. So Charlotte has written an algorithm here to basically, it looks at these peak positions and it says, I don't want to touch these things it's found, but other peaks which aren't where we're expecting the diode to be, it looks at how sharp they are and it can filter out, basically, it gets rid of the cosmic rays. So what this is doing is this is basically just some things that you can adapt. You can say a range where you don't want to remove cosmic rays. A reason we've done this is the SO2 peaks are extremely sharp and the algorithm can often remove them thinking they're cosmic rays. So these are basically the two things you're going to adjust depending on the intensity of your Spectra. And here we're saying that we're just going to save some figures showing how we've subtracted the cosmic rays. Okay, so let's run this filter and then have a look. So this is looping over all the Spectra, and what you can see is it's not looking in this purple SO2 region. What it is doing is in this Spectra, do you see this red dot? This y-axis is basically related to this value here, so you want to make sure these values are approximately the same as the y values on these plots. You can see that the algorithm has stripped away these cosmic rays where it's found them. So it has only found them in the spectra shown here, the others didn't have any. And for those that it did find, it stripped them away and it's resaved a spectra file now with _CRR to show that you've removed it. And this just makes filtering the data so much easier, otherwise those cosmic rays are going to cause you trouble. Okay, so now we want to inspect the peak parameters. And you might think, why aren't we just fitting all of the spectra straight away? And that's because the spectra can look really different, and we talk about this in the dyad fit paper. If you have weak spectra, you basically need to fit just the dyad. Once the spectra start getting stronger, the hot band and the dyad start to interfere with each other. And you're going to want to fit 2 peaks, because otherwise, if you don't fit that hot band, then the dyad peak isn't in the right place. As we get super strong, we're going to have to start fitting Gaussians to our data. And this is a problem. It takes a lot more time. So you don't want to fit Gaussians if you don't have to. So we're just going to have a look at our peak fit parameters. So the key parameters which can be really helpful is the position of dyad 1. This correlates really, really well with density, and we can see that actually, the approximate splitting and the approximate dyad 1 position just from that Scipy find peaks algorithm, they're pretty similar in here. None of these are really, really strong. It's not like 2 or 1 variations on the x-axis. You can see that we found carbon-13 peaks in these spectra, and we didn't find them down here. So these are all different ways that you could subdivide the spectra. And you can see all of the columns here that you could use to filter with. Okay, so the first thing we're going to do is on our instrument, we know that any splittings outside 101 and 108, approximately, they are garbage. So that might be that there was a fake peak from something else. It wasn't a dyad. We're going to want to get rid of that. We don't see any of those in our spectra, but this can be a really good way of filtering out really bad spectra, and they would appear here, the bad ones. So you can adjust that until you're happy with the ones it's chosen. Now what we're going to do is we're going to try and split our spectra into groups, okay? So to start with, let's look at dyad 1 positions, which is plotting a histogram. And you can see there really isn't much variation, less than a wave number. We might want to, we could write various filter criteria. Here are some examples that work quite well. In this case, we're just going to use filter 4. So we're going to take anything with a dyad 1 position greater than 1283. And we're going to use that. And that's going to be our only group, because there really aren't distinct groups in this spectra. You'll see some of the other examples there are. Here there isn't. Okay, so we're going to classify all of these spectra as weak. None of them have hot bands which are significant enough and raised up enough that we're going to need that Gaussian. It's not a big deal. Okay, if you had weak, medium and strong, you would want to add some filters in here so that you are comfortable that your medium ones and your strong ones are different, but not a problem here. We're then going to plot the group. So we see all of ours are weak in this example. And then finally, we're going to save that list. And that is step 2 done. So there are some other examples where you see that the filtering is more significant. For a lot of situations, you're just going to be using one group. You might have melting fusion vapor bubbles, all of which are going to be weak. You're not going to need to do these medium and strong steps. You might have just super dense fluid inclusions from xenoliths, in which case they would all probably be in that medium or in that strong category.